So I will just spend probably it will be quite short, maybe less than 20 minutes. So I just want to talk a little bit about graph cut. I guess so it is kind of a technique that I guess at least for the last decade have become kind of popular in a number of applications, like such as annotation and 3D reconstruction and so on. So I guess probably you heard of like mathematical mean cut. So basically, graph cut is trying to deal with this minimum cut problem, and there's a theorem that like basically the optimum solution of mathematical is same as mean cut. So therefore, like in practice, people typically is like construct a graph. Of course, they probably call some library, but what the library does is like to try to solve the mathematical problem and get the solution from the mathematical problem, and the solution will correspond to the mean cut problem. And I guess that before I even start, let me just maybe give an example. Let's say what I mean by this mathematical mean cut problem here. So let's say you have some nodes here. Let's draw like multiple nodes arbitrarily. Let's say I have I don't know, just like that. Let's say, and let's say I call this a source node, and that's a center node. So think of this as like some water flowing along a pipe, along some pipes, and let's say for each of these pipes they have some given capacity. Let's say I can have 5, 2, 4, 3, 1, 2, 1, let's say. So the mathematical problem basically is just want to try to find what's the maximum amount of this water can flow from the source to the main to the sink, even such a lateral side up. And it's kind of a dual problem. You'll be looking for, okay, this is a mathematical problem. Mathematical is trying to find the largest flow. So a dual problem is, I consider the same graph here. I want to look for cut. The so-called cut is basically, a cut is just something that you cause cut through the whole graph that separate the source and the sink. And then the value of the cut will be basically the sum of all these paths that the cut pass through. So for example, like for this particular cut, for that value will be like 1 plus 3 plus 2 plus 4, so it will be 10 here. And so apparently the mean cut problem is basically I just want to find the smallest cut. So let's say it seems that like the smallest cut will be this one. It's equal to 4.
Can you say how you find the 10?
No, I don't know.
Oh, okay.
I don't know yet.
Okay.
So a cut here is just saying, okay, this is one solution, one possible cut. So each cut will correspond to some value. And like for this first one, it will correspond to value 10 here. For this cut, will correspond to value 4 here. So then the mean cut problem basically just find the minimum, the cut will lead to minimum values, right? So, and for example, this one here, the minimum cut looks like it will be 4, and it turns out the maximum flow will also be 4 in this case here also. So there's a mathematical mean cut problem is proved by I think it's like multiple people focusing, and also independently by Sharon also, like Sharon and Alice and several other people. Alice, Sharon, and I forgot who is the third one. But anyway, actually the maximal mean cut theorem, okay, I probably won't talk about it today. If you write it down, it's just a extension of like, it's just a special case of derivative for linear programming. So you have two problems. If this two problems can be written as like linear programming, it's basically two problems to each other. So therefore, like the outcome would be just the same. So, but I guess like intuitively, I guess it's not too hard to see the Maxwell is equal to mean cut. So, but maybe if I have time, I will talk about that next time, sometimes later. But what I want to talk about is how to use this mean cut, basically graph cut, in image processing, and also like some very simple algorithm to do this Maxwell problem, to solve this Maxwell problem. Because if you can solve the Maxwell problem, then basically you also solve the mean cut problem. So for example, like if you have a solution for the Maxwell problem, in this case your maximum flow will be, let's say you get a solution, it's like this here. And then you will know which link is basically fully occupied, right? And the link that is fully occupied is basically the cutting point there. So therefore, if you find the Maxwell immediately, you know the mean cut solution. You can get the solution of the mean cut problem. Okay, so
excuse me, the flow is the going from the source to
source to the center.
Okay.
So just think of anything. Okay? For example, here the flow can be like you flow like 2 units through this link and then to this link, right? And then I flow 2 units from this link to this link. I also flow 1 unit from this link to this link.
Okay, so why max flow is
equal to mean cut?
Yeah.
That will take quite a lot of time, and I didn't prepare for that.
Okay.
But we can do next. Actually, it's not difficult if you know some optimization, because both of them are actually special case of linear programming, and they are just dual problem to each other. So therefore, it's just a special case of strong duality. So anyway, we may go to that like sometime later, but not today. But as I said, I just want to say that how to use that for this mean graph cut for like some image processing problem. So let's say, okay, I will just talk about one application, and it's pretty general. It's like for reconstruction. Let's say you have like 3D or 2D images reconstruction. So, but I will explain it with the 1D case first. Like if you understand the 1D case, then higher dimension is basically the same thing. So let's give an example here. If I have a 1D, think of like you have a 1D line here, let's say, and imagine that you kind of like have an actually if you think of like 1D reconstruction, it's kind of like a segmentation problem, right? So in the sense that you have some object here somewhere, let's say, and then like this object is like a 1D object, and you want to find out this 1D object here, and of course, if you have 2D, it would be something like you have a 2D object here, and it's also kind of like a segmentation problem, but you only have like 2 segments, basically, like foreground and background. You want to like kind of like cut out this object from the whole image there. So, but let's talk about this 1D case first. So for this 1D case, let's say I have some prior information about what's probable to be the interior of the object and outside of the object and also the boundary of the object. I don't know exactly what they are, but I mean very precisely, but I just have some belief or like some probability measure that, let's say, I have some value that, let's say I have something like, let's say, let me just draw something first. Let's say I have something like this. I'll explain what my number means here. So let's say what my number means is basically when the number is small, it means that like it's more likely that that place is a boundary. When it's big, then it's more likely it's interior or like outside. So or like basically like small value, so is likely to be boundary basically. So of course, like, if you look at it, this is a totally trivial problem, right? Because apparently I can just say, okay, this is my object. But if you extend this into 2D and 3D, it becomes much less apparent, right? Because if you have a 2D case, maybe you have a grid here. So you also have each of these from pixel to pixel. Let's say you have number correspond to like how likely is boundary or not. But then like, you really need a cut now, basically, to decide like, okay, where is the exact boundary or something like that. So immediately you can see like how why graph cut may help you to solve this problem here. So let's say, and then of course I can always find this value or map this value from let's say some observation, like maybe you start with some probability measure that what's the probability that something is likely to be a boundary, and then you just take an inverse to get this value. Yeah, stuff like that. Yes. So, but okay, let's have this now, and let's see how I use graph cut for doing that. So what I'm going to do is I will draw a graph here containing these nodes here. My graph will be like something like this. I will put a sink here at the two ends. So with very high load here, let's say like 1,000. This is not important, just a very high load. And then like I will put sink here. Oh, sorry, so this is sink. So I will put a source here. But actually it's not really matter, it's very source specific. I will just put link to each of these nodes here. I have too many. So like too many. And I will put a weight for each of these links. Let's say I put it 1. So, but okay, let's say it's alpha. Let's say alpha is equal to 1 first. I can adjust this alpha. Like I will explain why I want to adjust this alpha. So now I will apply the graph cut. So basically, I have a graph here. What if I try to apply graph cut? What do you see? Oh, wait a second. Maybe I made a mistake here. Let's see. Oh, okay, it's going. It's just maybe. Okay, so what do you see? Like, if I try, what do you think the solution here? Like, let's say if alpha is equal to 0.1, let's say.
What is alpha?
There is the weight for each of these links here.
And the numbers in the, was that 4, 3, 1?
Yeah, kind of.
The value of the each point?
No, the point is the link. Remember, you
okay.
are basically have a, yeah.
You wanted the max flow?
Oh, okay. Think of mean cut. Yeah.
Mean cut can be a line up, cuts 3 lines, and cut
Yeah.
line 1.
Basically, like mean cut probably have this solution here, right?
Yeah.
Yeah. And you see that naturally, like kind of separate. If you look at the solution, the part it cuts this part here, basically like automatically segment your target object from the background. And the alpha here is something that you can tune the size of your object. For example, if you feel like the object is to be bigger, you can increase the alpha here. So therefore, sometimes they call it ballooning force. Because if you look at that, if I increase the alpha, what happens is that it has a tendency that I want to cut less number of this here, right? So therefore, that automatically tends to make it cut like earlier. So therefore, then the object will become bigger.
Excuse me, why do you, for the cut, you just use the 1, 2, 3 from that side too?
No, I mean, okay, look at what's the solution here. If I cut like this, what's the value of the cut? It would be like 0.1 plus 0.1 plus 0.1 plus 1 plus 1 plus 0.1 plus 0.1 plus 1, right?
Oh, okay.
And you cannot get smaller than that, basically.
Yeah, okay.
Yeah. But if let's say if I make this pretty big, let's say alpha is equal to 10, then it will change the story, right?
Yeah.
Then it looks like the best solution will be something like I should cut once here,
Yes.
and then immediately go to here, and then cut here, and then cut here.
Must pass by the intermediate line?
No, just think of this as a cut. So how else you can cut?
1 plus 1.
But
Yes.
what's the value of that if I put it 10 here?
Or 10, 0.1.
Oh.
What's this value?
Okay, you're right. 0.1 is too small actually in this case, I'm sorry.
Well,
Yeah, I probably like, yes, that's
this
probably,
part.
yes.
Yes,
Yeah, 0.1 will be too small. So probably put 1 there, yeah. So then if you put 1, then probably will cut the white value. So if I put 0.1 there, I probably will, the ballooning force will be too small that I will basically just assume everything is the back one. So, okay, that's basically, that's how they do it. So if you extend it to 2D, okay, extend it to 2D will be something like this, right? So you have, now you have all these like intermediate link also, and then for each node, you all connect to a source here, and then for the sink, only the boundary will connect to your sink.
Oh, only the boundary of it?
Yeah.
Okay.
Yeah, only the boundary will connect to the sink here.
But
And
all
then
of the intermediate nodes connect to the source?
Yes. And then like your, again like all this like sink connection will be pretty big, set pretty big. And this you set it like is your ballooning force that depend on like how big you expect the region is. And then you can get a bigger or smaller region.
Okay, we are tuning the graph cuts with just to try and...
No, I guess the only thing you tune is this alpha here, right?
Yeah, the
So
alpha.
Expecting like how big is. So and actually the best thing to do it, I mean, this is more successful for this kind of algorithm is for high dimension. Let's say for 3D it would be like pretty cool, right? because for 3D it's pretty complicated if you're trying to solve the optimization problem there. Yeah, and for 3D, again, like, you can imagine how it should be, right? So for 3D,
inside.
so again, like for all the nodes, I need to connect to the source. This is very hard to draw.
And the percent boundaries?
And all boundary also need to connect to the sink.
Okay.
So I need all the nodes that is like yes. So okay, and that's basically the it's pretty short. So maybe I can talk a little bit how the mass flow algorithm. But actually, the mass flow algorithm turns out is pretty simple. The idea of mass flow algorithm is basically just you have, let's say, if you have a graph here, like let's say, I'm going to pick a graph. Let's say you have a graph like this. Yes, I have this is the source, and this is the sink here. So this algorithm, like, is called the Ford-Fulkerson algorithm. So basically the idea is, let's say if I have the length is like 100, 100, 100, 101. So it's a very simple idea. Basically, it's just trying to look for any path. So you will call a path as an augmented path. So at the beginning, like, let's say there's no flow in the whole graph there. So the flow is just all zero. And then like, let's say I will just arbitrarily pick a path. So let's say I pick a path like this. And then if I pick a path like this, then I'll just try to maximize this path. It's very simple to maximize the path. I just try to see like which link is like really capping the flow, and then therefore in this case, the maximum kind of flow I can allow will be like just one way. So then like after doing that, basically the flow will become like 1, 1, 1, let's say here, right? So now let's say like I remove, so okay, not exactly remove. So I have this new state of this graph here. And I try to look for another path that I can increase the flow. So now I cannot pick this path again because I cannot increase the flow again anymore. So let's say if I can find a path like this, again I can increase the flow. You see, but that's one of the paths here. It's actually one of the link here. I'm moving backward instead of forward. So actually, this one thing I should point out is like you can if you have a path, whatever path here, and if every link is going forward, then you can increase the path, or I can say you cannot increase the path if one of the link is already maxed out, have the mass is flowing at its maximum capacity. Let's say if the capacity is 10, if I already at 10 here, then apparently I cannot increase this path, the flow of this path anymore, because this link will kind of like limit the capacity, limit the flow here. But let's say I have another path, let's say it actually go opposite of one of the link there. So let's say the capacity is like 10, and that's showing 1 here. Let's say this is 1 and flowing 1 here. Do you think if I can increase the flow, or like, do you think this path is okay? Like in the sense, can I increase the flow of this path anymore? I guess I make it a little bit not very clear, maybe. So what to say is that I can, because need to be careful that if I am actually, if a path is going through a link that is going backward, then I increase this path basically will decrease the flow of that link, right? So therefore, like, if this link is actually currently flow 0.1, actually I cannot increase this flow here, because if I increase this flow, I basically am trying to decrease the capacity, decrease the flow here, right? So I will go negative here. But if it starts with something is 1, then actually I can increase this flow here. Because if I increase this flow, basically just decrease the flow of this link here. So, I mean, if I go back to here, it's exactly this example here. If this flow is actually, it looks like it may not be allowed because I'm already flowing at 1 here, right? But I need to also take into account that, like, I am flowing in 1, but my path that I choose is actually flowing opposite. So therefore, if I increase here by 1 here, I actually will decrease this here by 0. So that is allowed, that's okay. So after the second step, basically I will have this go back to 0, right? This go to 1 here, this go to 1 here. And then maybe I will try to look for a path again. If I'm kind of unlucky and look for this path again, then I will try to increase the flow again, like to the cap, then I will become 2, this become 1, this become 2. And then maybe next time I find this path again, I become like 2, 0, and 2 again. So I guess like this is a pretty bad case here. It looks like because I didn't find a good link, I should have just found this one, then I'm pretty fast. Only 2 steps and then I get a mass flow. But if I'm kind of silly, then I go like 200 steps, something like. So, but that's the basic idea of the Ford-Fulkerson. I mean, the Ford-Fulkerson algorithm didn't point out, basically it didn't give the detail like which path you should find. So basically, you just say, okay, you should just find a path if and see if you can increase the flow. If you can, just continue. If you cannot, then stop. So that's the algorithm. And about the same time, there's an Altman algorithm. That's basically, it's just the same as the Ford-Fulkerson, but it's also saying that I will just look for the path that is like is shortest. So we start with the shortest one and shorter ahead. So it's basically do a buffer search. So basically, like in that case, it will just look for a path like from with increasing distance. So then for Allen count in this case would be quite fast because the first time you look for is like you look for a path is length 1. I cannot find any path of length 1 resolves the same way. So there's no path. Then I try and find the length 2. Then I will find one of this path, let's say this one. And then I will cap the capacity. I will go all the way to 100, 100. Then I will do it again. And I find this one, and then 100, 100. Then I find the solution. So that's the basic idea of
graph code is the iterative algorithm, yeah?
Graph cut is actually solved by the mass flow problem in practice.
Okay.
Yeah.
So the
I
mass flow is the iterative, but
yes.
you mean that the
The solution is iterative, I guess.
yeah, for the finding the solution, we directly solve the max flow instead of the finding the curve. Yeah, just finding the minimum curve.
You have this basically, you're trying to find the mass
Yeah,
flow.
the minimum curve is just displaying for the graph card.
No, mean cut is a valid problem that in practice, like, people will use the mass flow solution to solve mean cut. It's easier. Of course, you can think of a mean cut algorithm. Let's say the dumbest one would be just like combinatorial, right? So you're just trying to, but it will be like really exponential, right? So how many cuts is possible, yeah. And then like you can try everyone, and then like you can call this an algorithm. That's fine also. Right? But in practice, it would be easier. Just consider the dual problem, basically the mass flow problem. Once you find the mass flow solution, then in this case, I probably will find the mass flow solution as, for example, let's say if this is 1 here, for alpha equal to 1 here, the mass flow solution I will find will be something like, let's say, I should put some direction here. So basically like this. Actually, that's pretty annoying when you know how the direction should go. Probably I shouldn't have any direction. So anyway, yeah, the mass flow solution probably will be, let's see, I have this one here, and I have this one here, one here, one here, and yes, and I have this one here. I mean, there's a flow like here, one, this one, actually this should be one here, and then I should have one somewhere here, one. I don't know, it's I guess let's forget it. I probably get stuck if I try to. But anyway, for simple case, this point here, your mass flow, basically. So yeah.
The cut value did not have a direction.
Yeah, I'm thinking right. You should
I
have
think you
actually.
have two sides. This side. The flow is from this side.
Yeah.
It's the cut value. And if the flow is this.
Yes, I'm thinking
value
about
may
it.
be
Doesn't,
different.
yeah, this shouldn't have should be undirectional here.
All the directions.
Yeah, should be like allowing both directions. Otherwise, it yeah.
So how about 2D? How you can find the direction in the 2D?
Actually, I guess it's easier. Like, forget about the direction here. I mean, the direction is easy to explain this algorithm here, but if you think of that, you don't really need direction, right?
I think for the
Think of that when you have a source and
for
sink,
the
and trying to find the flow problem, like from a source to sink. Just think of the pipe can go either way, but if you have the biggest flow from source to sink, then again still you have the mass flow solution will be equivalent to your mean cut solution, in the sense that when you have mass flow, then the flow, then the link that with the maximum capacity will correspond to your the cut, the length that you have to cut. I mean, let me repeat it. Like when you have the mass flow solution, so for all the link that have achieved the capacity, it will correspond to your cut. And if you have just a flow problem from source to sink here, let's forget about the direction here. You have to have, if you have the solution already, you have to have and let's say just as I said, like if you build a cut by connecting all the link that achieve the capacity, I would claim that would be a valid cut. Valid cut in the sense it really separates the source and the sink. If that is not the case, then I always can increase the flow a little bit more. I mean, it's, for example, like, assume that it's not a valid cut, that means that there will be a link here that I don't have, basically I didn't cut through that link. So that means for that link, I will have, or like along that path, I will have no link that achieve capacity. Then apparently I haven't achieved the mass flow yet, right? Because I can always increase the flow along the path there, and then one of the link will saturate, right? And then when that link saturates, basically that link will satisfy what I just said. That will be the one that achieved the capacity, and therefore I should cut through that also. Yeah. So anyway, it's just some intuition, but yeah, you can see that. Okay. Let's forget about the direction. I mean, just for sake, if you achieve the mass flow there, then apparently you have a mean cut solution. But of course, like, yeah. I mean, lots of people consider this problem here, like this is like the most primitive one. They say maybe in the 50s. So I guess that eventually most likely we just call libraries because so you if just for computer vision research, I guess like your focus will be mostly on how to build this model here and then apply the library. But I guess it's kind of like useful just give a value.
This path you choose the arbitrary at first. Arbitrary path.
Oh yes. Okay, count is not count arbitrary. Choose the shortest one. One shortest one. Of course, you have two shortest one here, but the shortest one that you can increase the flow.
Oh, shortest path.
Yeah, shortest path. So we start with basically do a buffer search.
Both sides have the same distance.
Oh, in this case, will be like because this path and this path are the same distance. So the distance is just count the number of link as distance. So this will be 2. This will be 2 also. Yeah, so you pick the shortest one and then yeah.